In the remaining time, let me say something about Fourier series. Okay, so Fourier series is, well, we've got functions. We've got a function f of x. And we want to write it as a combination of, maybe it has a constant term, and then it has some cosine x in it, and it has some sine x in it, and it has some cosine 2x in it, and some sine 2x, and forever. So what's the difference between this type problem and the one above it? This one's infinite. But the key property of things being orthogonal is still true for sines and cosines. So it's the property that makes Fourier series work. So that's called a Fourier series. Better write his name up. Fourier series. So it was Joseph Fourier who realized that, hey, I could work in function space. Instead of a vector v, I could have a function f of x. Instead of orthogonal vectors, q1, q2, q3, I could have orthogonal functions, the constant, the cosine x, the sine x, the cos 2x, but infinitely many of them. I need infinitely many because my space is infinite dimensional. So this is like the moment in which we leave finite dimensional vector spaces and go to infinite dimensional vector spaces, and our basis, so the vectors are now functions. And of course, there are so many functions that we've got an infinite dimensional space. And the basis vectors are functions too. A naught, the constant function 1. So my basis is 1 cos x, sine x, cos 2x, sine 2x, and so on. And the reason Fourier series is a success is that those are orthogonal. Okay, now what do I mean by orthogonal? I know what it means for two vectors to be orthogonal. Y transpose x equals 0, right? Dot product equals 0. But what's the dot product of functions? I'm claiming that whatever it is, the dot product, or we would more likely use the word inner product, of, say, cos x with sine x is 0. And cos x with cos 2x, also 0. So let me tell you what I mean by that dot product. How do I compute a dot product? So let's just remember, for vectors, v transpose w. For vectors, so this was vectors, v transpose w was v1 w1 plus vn wn. Okay, now functions. Now I have two functions, let's call them f and g. What's with them now? The vectors had n components, but the functions have a whole, like, continuum. To graph the function, I just don't have n points, I've got this whole graph. So I have functions. I'm really trying to ask you, what's the inner product of this function f with another function g? And I want to make it parallel to this the best I can. So the best parallel is to multiply f of x times g of x at every x. And here I just had n multiplications, but here I'm going to have at a whole range of x's. And here I added the results. What do I do here? So what's the analog of addition when you're in a continuum? It's integration. So that the dot product of two functions will be the integral of those functions dx. Now I have to say, well, what are the limits of integration? And for this Fourier series, this function f of x, if I'm going to have, if that right-hand side is going to be f of x, that function that I'm seeing on the right, all those sines and cosines, they're all periodic with period 2 pi. So that's what f of x had better be. So I'll integrate from 0 to 2 pi. Everything is on the interval 0, 2 pi now. Because if I'm going to use these sines and cosines, then f of x is equal to f of x plus 2 pi. This is periodic. Periodic functions. Okay. So now I know what, I've got all the right words now. I've got a vector space, but the vectors are functions. I've got inner products, and the inner product gives a number, all right. It just happens to be an integral instead of a sum. Then I have the idea of orthogonality, because actually, let's just check. Orthogonality, if I take the integral, let me do sine x times cos x, sine x times cos x dx from 0 to 2 pi, I think we get 0. That's the differential of that, so it would be 1/2 sine x squared. Was that right? Between 0 and 2 pi. And, of course, we get 0. And the same would be true with a little more, some trig identities to help us out, of every other pair. So we have now an orthonormal infinite basis for function space, and all we want to do is express a function in that basis. And so the end of my lecture is, okay, what is A1? What's the coefficient? How much cosine x is there in a function compared to the other harmonics? How much constant is in that function? That would be an easy question. The answer, A0, will come out to be the average value of f. That's the amount of the constant that's in there, its average value. But let's take A1 as more typical. How will I get, here's the end of the lecture then, how do I get A1? The first Fourier coefficient. Okay. I do just as I did in the vector case. I take the inner product of everything with cos x. Take the inner product of everything with cos x. Then on the left, I have the inner product is the integral of f of x times cos x dx. And on the right, what do I have? When I say take the inner product with cos x, let me put it in ordinary calculus words. Multiply by cosine x and integrate. That's what inner products are. So if I multiply that whole thing by cos x and I integrate, I get a whole lot of zeros. The only thing that survives is that term. All the others disappear. And that term is A1 times the integral of cos x squared dx, 0 to 2 pi, equals, so this was the left side, and this is all that's left on the right-hand side. And this is not 0, of course, because it's the length of the function squared. It's the inner product with itself, and a simple calculation gives that answer to be pi. So that's an easy integral, and it turns out to be pi, so that A1 is 1 over pi times this integral. So that's Euler's famous formula for or maybe Fourier found it, for the coefficients in a Fourier series. And you see that it's exactly an expansion in an orthonormal basis. Okay, thanks. So I'll do a quiz review.